A white dwarf is what stars, like the sun, become after they have exhausted their nuclear fuel. Near the end of its nuclear burning stage, this type of star expels most of its outer material, creating a planetary nebula. Only the hot core of the star remains. Something extremely fascinating to me about the white dwarfs are their link to type 1a supernovas. You may know about them, you may not. If you don't, hold your horses, we'll get there. So, first and foremost, 99.9% or more of the stars in the whole universe will become a white dwarf. That's just the way it is. They get really hot, their fusion, all that, and then all of a sudden it just gets to the end of their life and they burn out, the shell goes out into space, boom, and all you have is the core. And what's left in that core is completely carbon. Okay, so it's just carbon. Now, a typical white dwarf is about the size of the Earth, okay? But on average, they have half the mass of our sun. So imagine a body in space that is the size of our Earth, but that body has half the mass of our sun. Now, they can even get smaller. So the smaller they become, the more mass they have. So imagine a body, say, the size of Mercury. That could potentially have the mass of even more than our sun. So you can just, picture in your head how heavy and how, massive, even though they're not huge as in diameter, but they're just so dense and heavy. Okay, so speaking of dense, that's where the type 1a supernova comes in. So first off, the material on a white dwarf, okay, the density of that is 1 million times the density of water. Okay, so you take water. To give you a better example, so lead, in pencils, lead is 11 times the density of water, and lead is pretty dense. Okay, so imagine the materials on a white dwarf being 1 million times the density of water. That is extremely dense. Okay, and to add to that, the gravity on a white dwarf. Okay, so if you take the gravity that pushes on us every day on our Earth, okay, you take that gravity, but what's on a white dwarf is 200,000 times that force of gravity. So that force is just pushing on that white dwarf with that, that dense material, just pushing. Okay, so if you take 1 teaspoon of material from a white dwarf, it will have the mass of an elephant. So and that's just 1 little teaspoon. It's a very dense material. So, you take all the you take the pressure, you take the gravity, you take all this stuff. What is holding it back? Why doesn't it just collapse into itself? It's something called electron degeneracy. Basically, what that means is the electrons in the atoms on the white dwarf. So you have the atoms, the electrons in those atoms need their own space. Therefore, they push back against the pressure. Okay, but they can only do this for so long. It goes billions, and this is a course of billions of years. So over billions and billions of years, all this pressure is pushing against, and all of a sudden it'll snap and get to the point where electron degeneracy can no longer hold its own. And that's when a type 1a supernova happens. Basically what happens is just mass just gets blown into the universe, just so much material, carbon, everything, and that's what's to believe happened and how we have carbon on the Earth and in our solar system. These supernovas are massive. They just generate energy and materials into the universe and spread them all over the place. There's so much more about white dwarfs that I did not cover, but this was one of the topics about the white dwarf that I found the most interesting. There's so much more to be told about white dwarfs and, of course, the universe.